Okay, in this video, we're going to work through a bunch of examples of problems that relate to Lesson 5, which was probability of compound event and cases and the related special case of independent events. Okay, so let's take a look at this first problem. It says a jar holds 10 white, 6 red, and 4 blue marbles, and if 2 marbles are chosen with replacement, which means we draw a marble out, record its color, replace it, and then draw a second marble out after randomizing the jar again, what would be the probability that both marbles that we draw would be red? Okay, so pause the video, give this a try, and then unpause. Okay, so this is how we would start the problem. First of all, we're talking about this is the situation in the jar. We have 10 white marbles, we have 6 red marbles, and we have 4 blue marbles, which is a total of 20 marbles in the jar. So if we're talking about finding the probability that the first one is red and the second one is red, then that's the same as using an AND case, right? Because we have to have first one red and, right? This symbol means and, second one red. We know that with AND cases, we multiply probabilities. So the first one would be the probability that the first one is red. But then we multiply by a second probability, and this has to be the probability that the second is red, but given that the first one's red, the second one always has to be a conditional probability. So it'd be the probability that the second one is red, given that the first one is red, okay? And so now we can compute these. So the probability that the first one is red, we have the jar like this. We have 20 marbles in it, 10 white, 6 red, and 4 blue. And so each of these is equally likely to be drawn. So this is an equally likely situation. We can represent this with a fraction. And on the bottom, we'd talk about all the possible marbles, the entire sample space. So there are 20 marbles there that we can draw from. And then we're talking about the probability of being a red, and 6 of those were red. So 6 out of 20 would be red. That'd be the probability of getting a first red on the first marble draw. Okay, so then we're going to multiply the probability that the second marble is red given that the first marble is red. So given that the first marble is red, so we have to reconsider the situation. Let's actually, I'm going to change colors for this one. We're multiplying by another probability. So let's consider what after we draw, so after the first draw, what do we have? Well, because we're replacing, this is with replacement, that means that we'll still have the original 10 white, all 6 reds, and 4 blues, and therefore 20 marbles. And so that means the second time around, we have, again, 20 marbles, and 6 of those are red. And so it would again be 6 out of 20. So that's the same. Now, what that means is that the probability of the second being red, given that the first is red, is really the same as just the probability of the second one being red. And it doesn't really depend on whether the first one is red because we replace the marbles. So this is a special case where they're really independent, but we can always write that second one as a conditional probability. And so this turns out to be 6 times 6 on the top, which is 36, 20 times 20 on the bottom, which is 400. And in a calculator, that turns out to be 9%. So that probability would be 9% that we would get 2 red marbles in that jar if we replace the marbles. Okay, let's move on to the second one here. It's almost the same problem. The jar holds the same 10 white, 6 red, and 4 blue marbles. We draw 2 marbles this time without replacement, and we want the probability that both are red. So the same situation, the only difference is we're not putting the first marble back before we draw the second marble. So same thing. First, we have 10 white marbles, 6 red, 4 blue. That's 20. So the probability that the first is red and the second is red is going to be the probability that the first is red times the probability that the second is red given that the first is red. Okay, and the probability that the first is red, just like in the last problem, is there's 20 possible marbles. 6 of them are red, so 6 out of 20. And then we have to consider the second one, which is the probability that the second one is red given that the first one was red. So if the first one was red and without replacement, we don't replace without replacement, then this is what's now in the jar. We still have the 10 white marbles, but now we have only 5 red marbles, and we have 4 blue marbles for a total of 19 marbles in the whole jar, right? So that means out of the 19 remaining marbles, 5 of them are red, right? So the second conditional probability now has changed because we didn't replace the marbles, so the situation in the jar is different. And again, we would multiply these two things, and so the answer would be 30 out of 20 times 19 is 380, and so that is 0.0789. A little bit different probability than the first time where we did replace. Okay, so kind of a classic jar problem. Let's take a look at the third one here. It says a fair 10-sided die is tossed 3 times. What's the probability that we get a 7 all 3 times? All right. Well, let's see. If we toss a die, hopefully you'll agree that every time we toss a die doesn't really have any memory, right? And that means that we have the same probabilities occurring for every individual, what we would call a trial, every time we toss this die, right? So maybe I could write it this way. I could say the probability that all 3 tosses are 7, all 3 are 7, I guess I should say, all three are 7, is the probability of the first one being 7 times the probability that the second one is 7, given that the first one was 7, times the probability that the third one is 7, given that the first and second are also 7. Okay? Really, those should all be multiplied together, but they're also conditional probabilities, given that the things that had to happen first happened. But because the die tosses are independent, that means the probability of getting a 7 is always the same all the time. So really I could say that this is just equal to the probability of getting a 7 times the probability of getting a 7 again, because the probability of getting a second 7 doesn't really depend on what happened at the beginning. It doesn't matter if it's a 7 first or not. It's just the probability of a 7, and then times probability of a 7 again, right? So let's figure out what one of these probabilities of 7 are. Since each of the sides of the die are presumably equally likely, the sample space would be the list of all the possible answers, right? We have 10 sides, so we could get a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, or a 10. And the event would be that we get specifically a 7, right? So this probability of 7 here, right, would just be 1 of the 10 cases. And then this one here would be 1 out of 10 again, and then this one here would also be 1 out of 10. In each case, we're talking about 1 out of the 10 cases. So it'd be 1/10 times 1/10 times 1/10, which is 1 over 1,000, which would be 0.001. So very unlikely indeed, 0.1% chance of that happening, where we would get a 7 all 3 times if we toss a 10-sided die 3 times. Okay, so hopefully you're pausing the videos and trying these on your own, and then unpausing and seeing how they, whether or not what you got matched. Let's take a look at another case here. All right, so in this one, it says a sample of 100 people at a mall were asked to try 2 different soft drinks and state their preference. The results are shown in the table. So we have drink A and drink B, and we separated the responses of the males and the females. So 22 males said drink A, for example, and 18 females said drink B. Okay, what's the probability that a person selected at random from this group will prefer A, will be female, is a male and prefers B? So these are different kind of combinations of things here. So, well, whenever we're given a table like, actually, go ahead and pause the video, give it a try these, and then unpause. Okay, so whenever we're given a table like this, the first thing we should always do is go ahead and add up the columns and the rows, because typically we need those numbers. So 22 and 22 is 44 total people that answered A. We have 38 plus 18 is 56 people that like drink B. We had a total of 22 plus 38, which is 60 males, and we had a total of 22 and 18, which is 40 females, which means we have 100 people total. So it's always a good idea to add up the rows and columns just to make sure that you have totals there. So now let's take these one at a time. The first one, A, says what's the probability that a person selected at random from the group will prefer drink A? So there's no sort of condition here or anything like that. It's just a simple probability. If I were going to write the statement, I might write it this way: the probability that the person likes drink A. Since that's not a conditional probability, it's what we call a simple probability, right? And we're equally likely to choose any person out of these 100 people. This is an equally likely case. right? But the bottom would represent all 100 people. So out of all 100 people how many total liked A? Well, that would be everyone in the A column, which is 44 out of 100. So that would be 0.44, so 44% chance of a person liking A. Okay, let's take a look at part B then. Part B says, what's the probability that a person selected at random from this group will be a female? Same kind of thing, probability that the person is a female. Okay, that is also a simple probability, which means we're considering all of the students in the sample. So that would be 100 students, and out of those, it looks like 40 of them were females, and so that would be 0.40, so a 40% chance of being a female. So far, so good, not too hard so far. C says, what's the probability that a person selected at random is a male and prefers drinking B? Okay, so male and B. Well, that's actually a specific place on our table, right? One particular number here. You have to be in the male row, and you also have to be in the drink column here. So that would be this right here. 38 people are male and prefer drink B, right? 38 people. So it's still a simple